Alright, draft physics video. Probably the last part in this little series of videos. So we'll finish this up, this gravitational wave thing video, and I'll just make the points where they need to be made and blah blah blah. But this isn't very complete science, certainly at minimum. So I also notice they did change this equation. They not only changed the 21 in the approximate, and I don't even know what this means. Distance divided by light years? I don't know. M divided by M sun. So what solar? Is this what this M is in? Solar masses? I don't know. But anyway, continuing.
And Ray Weiss of MIT drew this sketch on the bottom left in an internal MIT journal, and together with Ron Drever, Kip Thorne, and many other important players, they put together the Laser Interferometer Gravitational Wave Observatory, LIGO. Now, it's a little glib to do this in one slide and say...
Yes, 40 years, $1 billion, and 1,000 scientists later. So $1 billion spent on this.
40 years, $1 billion, and 1,000 scientists. So I want to take some time to really emphasize how amazing this project is. As I'm going to describe in the rest of my lecture, this experiment has made a real breakthrough, the likes of which comes along, in my opinion, once every 100 years at most. This is a real breakthrough. And this experiment really was 40 years in the making.
Alright, so let's understand. It's just receiving little special signals from stars very far away. Little special signals. So let's understand. It's shooting a very powerful laser. So it's not like they just shoot a little tiny green laser. Now it's like a gigawatt, huge, powerful laser they're shooting at the mirror. So we're supposed to believe that the energy of the laser being shot at the mirror doesn't distort the mirror, but the energy coming from 5 billion light years away, an event, that they can see. It sounds a little implausible. It seems an extraordinary claim, and are we given extraordinary evidence? No. Are we given ordinary evidence? That is, somehow some details and some, like where they actually use this interferometer to see some other event, like when they shot a probe into the moon and blew a big piece of it out. You know, it wasn't very big, but you know what I mean, an explosion. Did it see that? Did it detect it? What has it detected?
And the National Science Foundation and research universities in the U.S. provided all the seed funding for the initial prototypes. The NSF picked it up and funded it starting in 1994, and over 20 years they kept it going over changes of Congress, changes of administration, changes of NSF program director. Everybody had the vision.
Yes, a huge pile of money was thrown into this thing, and we're to expect that there wasn't any pressure for them to produce something. No pressure at all.
To see this risky but high reward project through, and we should...
Alright, and the high reward is what? We get to make up a whole bunch of new stuff about how the universe works. And that will lead to many happy people. I don't think so.
Be proud as American taxpayers that through our elected and appointed representatives, we supported this project.
Now, it'd be nice if they supported some science that was actually scientific.
So, what is LIGO? There's two LIGOs. There's one in Washington State. There's one in Louisiana. And you can kind of make out that there's a lot of tubes. In those tubes are lasers. It's the Laser Interferometer Gravitational Wave Observatory. Let me tell you why. This device is called a Michelson interferometer. This is something that here at the U of A we teach our undergraduate physics majors in the second year of their study. So it's not something I can fully explain in the next 3 minutes, but I can give you the gist.
Yes, right. And the gist will ignore certain details.
The basic idea is you shine laser light out, you split it up, and then it bounces off mirrors and gets recombined.
Right. So let's understand this splitting concept. So this in itself is sort of a dicey bit of engineering, these beam splitters, because any defects they create, one path of light, the defects go this entire distance this way, all the way back, and then reflect. And the other path, no defects, no defects, no defects, and the defects are only created now. So one path has very short distance of defects, the other path has a very long distance of any defects. So, but it's the whole idea that they think this thing is a little piece of magic, and it doesn't cause any changes. It just perfectly splits the beam in two. That's their assumption.
And then as a wave wiggles those mirrors, the amount of light read out changes. The reason you can do this is because light is a wave. Light has peaks and troughs.
Yes, well, it doesn't. So,
And when two beams of light meet, if those peaks and troughs line up, then you get more light. It's brighter. But if those peaks and troughs anti-align, as shown here on the right of your screen, you get no light at all. So, whether the peaks and troughs are aligned or not is a very sensitive function of the...
yes, well, it's called frequency, and whether it's in phase or out of phase can be detected, yes. So if the photons are all peaking here all together, then that's in phase. If they're peaking from one branch here and then the next branch peaks here, then that changes the phase and subsequently the frequency, in a sense, of the light.
The distance the light has traveled in this setup. And so as the wave comes through and wiggles those mirrors, the peaks and troughs change their alignment, and the light read out on the...
Right, so again, this beam is very powerful. It doesn't wiggle the mirrors. Only the things 5 billion light years away wiggle the mirrors.
Right of your screen changes in time. That is the light that LIGO actually measures in order to measure the changes in distance of the mirrors as that gravitational wave washes through. Here's LIGO in a kind of CAD drawing. It's the same concept, but with lots of bells and whistles. These tubes are in vacuum. It's a very large vacuum. And there's all kinds of tricks they play to increase the power in the interferometer and to...
all kinds of tricks. Oh, isn't that wonderful?
isolate it from sources of noise. That's really the hardest part of this whole business. You're trying to measure distance changes of less than a proton diameter. How do you do that when a truck could drive by and wiggle your mirrors by way more than a proton diameter, or an earthquake could happen? What do? You need to be isolated from environmental noise somehow. And the way they do it is as follows. They have this amazing gizmo, this 4-stage pendulum, which you see the design for on the left and some photos on the right. And this provides two kinds of isolation. There's active and passive. Passive isolation is like the shock absorbers in your car. When you drive over a bump, the bump hits your car pretty hard.
Yeah, so it isolates all the big movements, the slow ones, passively, without doing anything. Active. Active means you're canceling it out using computers and such.
But you don't feel much of that bump because there's springs in your car that damp that out and give you a smooth ride. They use that kind of passive noise isolation. And they also use active isolation, which is like your noise-canceling headphones. When you put them on and turn on the power, they actively cancel out incoming sound waves. Similarly, they actively drive this system to cancel out any incoming vibrations in the ground that it's attached to.
Right, and instead of using those to point out how sensitive their instrument is, or showing some tests demonstrating how sensitive it is, not with that.
Now this talk has a lot of eye candy, a lot of really nice pictures, movies, but I have to tell you, this is the slide that still gives me goosebumps. I remember vividly, almost a year ago exactly, when this slide was released in a press conference at the National Science Foundation, which I...
Alright, so let's understand. These little jiggles are supposed to be, so there's noise in the signal, so we're to accept that there's going to be some erraticacies in it. But this is supposed to somehow represent the cycling of these two objects. And as they cycle faster, the bands get tighter together. And the amplitude would represent how much gravity they're producing. Okay.
Streamed here at the U of A for students and faculty and anyone who is interested. And when I saw that signal, I thought, oh my gosh, that's a gravitational wave. Now, for you, it may not jump out to be a gravitational wave so obviously, but let me explain to you why. But before I do that, the most important thing about this plot are those numbers on the top left, GW150914. That is 2015, September 14th, my birthday. The gravitational waves arrived on my birthday. Thank you, universe, for that birthday present. No.
Not all so special.
Okay, that's only the most important part of that slide to me. To the rest of you, let me take you through it. First, look at the vertical axis. It says strain, that's that fractional stretching and compressing, and it says 10 to the minus 21. This is from the scientific paper.
Yes, right. Yeah, this is from this. It's a scientific paper. We say so. Didn't you see it in the scientific paper? I mean, the scientific paper says so. So shit, this must mean something. Yeah. So that's the proton. So this is the mirror got deflected a proton.
They did it. They measured those wiggles that you see in red are changes in distance of a part in 10 to the minus 21, less than a proton diameter. the x-axis, the horizontal axis, is time. Notice all this happened over just a fraction of a second.
Yes, so and the new one happened over 100 seconds. So somehow there's great variance in how these big heavy things spin into each other. These little heavy things spin into each other. They can do it really fast, less than a second, or they can do it really slow, 100 seconds. Sure, why not?
Now let's look at the red signal. The red signal is what the device in Washington State measured. That's the readout, which represents the changes in distance of the two mirrors. Is that a gravitational wave? Is it a truck driving by? Is it an earthquake? How do we know? Well, on the second slide, you see that same data on the right overplotted with the data from the other observatory in Louisiana, all the way across the U.S., and they line up perfectly. There's no way that the same truck drove in front of Hanford.
Well, could it have been the same earthquake? See, he said earthquake and truck, and then he only debunks truck. He doesn't in any way explain how it couldn't have been an earthquake. You know, an earthquake in, say, Java or underneath the ground, 10 miles under the ground in Bangladesh or something. Couldn't possibly have been that. Oh yes, that's exactly what it could possibly be in. There's no theory to say, oh no, it can't possibly have been some sort of natural burp. Oh, except that the theory is that their filters have already eliminated every possible fart noise the Earth ever makes. It's already recorded every sound that can possibly be made by the Earth and any surrounding space, even the sun. It's got all those burps and all those belches all figured out already, and so it's never surprised. Sure.
And drove in front of Louisiana at exactly whatever it is, 3 milliseconds apart, the time for the gravitational wave to come from one to the other in exactly the same way. They did a bunch of fancy statistical analysis to put some numbers to say that, yes, that's not what happened, and yes, that's really a gravitation.
Right. So they eliminated truck. Did they eliminate everything else? We'll just have to take their word for it, huh? The $1 billion they invested, and we'll just have to take their word for it.
Gravitational wave. But this is why I knew right away when they put it up on screen that this was a gravitational wave. This signal was so loud that you didn't have to do any of that fancy statistical stuff. It just says, wow, gravitational waves from outer space.
Yes, I don't think that's what it says. And it was so loud, so let's just understand, if it was photons, if the object way far away had, instead of creating gravity, created light, it would have fried us. This far away. That's how much energy had to hit the Earth.
When we physicists try to understand these signals, we often convert them to sound. It's a quick way to get all the information about amplitude and frequency.
No, I mean, if that's what you do for your own sake, you're silly people. So this is this is how hythloday thinks a real scientist approaches this, is that I have to turn something that's completely understandable as a frequency into a sound, or I can't understand what it is. And it won't be its real sound, it'll be a fake sound in the sense that I'll change the frequency so it's audible. Isn't that special?
Frequency. So now I'm going to play the sound for you, and you're going to hear a bit of a thump. That's what it sounds like if you just take the frequency of the wave and convert it to a sound wave at the same frequency. Then you hear that thump twice, and then you're going to hear the same sound but upshifted into a frequency range where your ear is more sensitive to the features.
Yes, we've just completely distorted it. Some more distorto evidence. Let's present some more distortion evidence at the trial. We're going to convince you this is real, and here's our evidence. Distortos. Oh man, that was so impressive. Whoa! Oh man, I gotta hear that again and again. Oh! Ah! Ah!
So that little... We have a name for that. We call it a chirp.
We chirpy it, yes. Because you're all, this is just like their little strange and their happy quirks, and this is so serious science. It's kindergarten.
That chirp's going to come back in about 10 minutes, so let's remember that name. Let me play it for you again in case you missed it. Again, the first thing you hear is a thump. That's the actual signal, and you're going to hear that twice. Then you're going to hear the upshifted version.
Oh, more. Bloop, 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 bloop. Holy, I heard a bloop. I'd call it a bloop. I wouldn't call it chirp. I'd call it bloop. It's bloopy. bloop.
Those are the waves from a binary black hole, that two black holes that merged 1.3 billion years ago, 1.3 billion light years away.
Says Spanky.
It came all the way across the universe.
Yeah, I said so. That makes it true. Because I said so.
How do we know these are actually merging black holes, like I said?
Yeah, how do you know? It's because you made up a bunch of crap that says this is what black holes look like. See, that's what they look like, and that's pretty similar. So that must be the same thing that we made up. Don't you think? Mostly. So the funny part is this part, right? So this is their theoretical. Something's happening to the black holes and they're going to crash into each other, so they're accelerating a little bit faster, but these are only one single cycle. So again, how do you even can make any sense out of it? You really can't. And somehow they're creating this extra strong signal. See, they weren't creating any signal here, they were spinning around each other over here. No signal. See, no signal, there's nothing, no protons getting moved. And all of a sudden, at some stage, they start moving a whole bunch of protons, and a lot of them. And before they crash, the crash isn't much bigger than the rest. The bloop isn't much bigger than the rest of the signal. So, what's the theory of that? How are they creating the gravity while they're still spinning? How are they converting the solar masses into gravity as they're still spinning?
Well, again, they did a lot of fancy statistical analysis, but for this signal, it was so loud they really didn't have to. Again, this is a snapshot from the scientific paper. On the top
So it's from their paper. I mean, they wrote it, so this must be how it all happened because they wrote it. The people $1 billion in the hole with no results.
line, you see the same two plots that I showed you before, the data from one interferometer on the left and the two stacked on top of each other on the right. On the second line, you see a theoretical prediction, a calculation from Einstein's equations of what the waves look like.
Subtract the two, just noise. So I like that. That's sort of interesting. You know, the noise signal, which also has some duplicate pattern.
If two black holes merge. And then when you do, you subtract the two. You subtract the prediction from the model, and what's left should just be noise, and that's on the bottom. So you see right away that, what is this? It's the normal noise in the interferometer plus a signal, which is merging black holes. Now the way these theoretical calculations are done is by a supercomputer. We take the equations that Einstein wrote down in 1915, and we solve them on the state-of-the-art supercomputers. Here's a simulation of the orbiting and merging black holes of the same size and distance from each other that was...
Okay, right. And so all you have is two little gravity wells. There's no evidence that there's supergravity created anywhere in here at all. Little wells, inverse square law, can't even tell the difference. Theoretically, I could put these two heavy objects and you could... Let's see if I got a piece of blank here. Yeah, here's a piece of blank. Okay, so here's the theory. So say there's 60 solar masses, so there's 30 and 30, so there's 60 solar masses here. And I draw a circle around it that's the size of, say, 1/4 of a galaxy. Well, that same circle that's 1/4 of a galaxy, let's say, would have 1 billion stars in it. Alright? So it would have 1 billion solar masses in the same size circumference. Alright? Now, their theory is that somehow this little thing here is going to produce so much more gravity than this billions of suns here in the same arc. Somehow these two things and the gravity they're producing, this one's going to outshine this billions of suns is going to have less gravity than this 60 suns. Somehow their theory allows for that. Not just a little, not a little bit more, a hugely more gravity.
Measured by the LIGO experiment. Now you see the black blobs and the tracers, that's just to orient your eye as to what's going on. All the interesting information is in the arrows and the colors.
Right, so nothing happened in these arrows much, okay? There's just a little bit of acceleration happening. Is there? For what reason? Who knows? Somehow they're getting more gravitational? No, that can't happen. There's no Einstein theory for that.
And the shape of the sheets below them. That's representing the curvature of space-time. You'll see.
Yeah, well, I didn't see this part of space-time curving any, so certainly there's no event happening that's all that dramatic yet. There's nothing out here is changing, and somehow it has to change out here for it to change 5 billion light years away. So this is another useless piece of crap graphic.
Now the simulation will slow way down near merger, so you can see just how distorted space-time is getting. It's like a storm.
Alright, so let's understand, way before merger, we're already receiving these very powerful waves, and now all of a sudden their little orientation lines are creating this crap. Whatever this crap is, all of a sudden showed up in the animation. So all of a sudden there's something extra happening.
In space-time, as the black holes finally merge and there's really some cuspy, sharp features, there's a burst of radiation, and then the waves are...
Burst of what kind of radiation? So the burst of radiation in the newest event happens 1.7 seconds after the merger.
Off on their journey across the universe through LIGO.
Right, so let's just say that again. You know, the waves of the merger. No, the waves have to be before the merger. You can't have the, what did I call it? The blip or whatever, the bloop. You can't have the bloop, okay? If you know, if you don't have the signal going up to the blip, the bloop.
In space-time, as the black holes finally merge and there's really some cuspy, sharp features, there's a burst of radiation, and then the waves are off on their journey across the universe.
And then the waves are off on their journeys. That's what he says, right? Clearly the waves had to be off on their journey before the event, not after the event. That's how they receive the signal. So the waves, the solar masses are getting converted before the event. After the event, there's almost nothing that happens gravitationally. So, yeah, he didn't describe it correctly, obviously.
Here's another fun video.
Okay, fun videos. So that's always good evidence to build a case scientifically, is to make fun videos. And if you happen to have a blender, you can make one of these. Yeah, that's how they do this. They put shit in a blender and then videotape it. Yeah, that's actually how they do it.
This is the question. Suppose we were actually near these black holes and we were watching them in a spaceship. What would you see? Well, mostly you see the stars behind you. And you don't see any stars from where the black hole is because all the light has been swallowed up by the black hole. But you also see a very distorted pattern of stars because the black holes bend the light.
Yes, and this one's slowly spinning. So they think spinning does something too. These things change their whole behavior when they're spun. Well, he'll get into that, which is horse shit. Complete horse shit.
So the stars don't look like their actual positions. They look very distorted. And I think we'll just watch the end of this beautiful movie together.
Yes, it's a beautiful movie. Isn't that special? So they showed us a beautiful movie, and that's, you know, juries should always be shown beautiful movies. You know. Pathetic.
Let me tell you what they actually measured for this system. It's not about just detecting gravitational waves. It's also about doing astrophysics.
It's about making shit up about, well, look, what do you think? Well, I think it's 30. What do you think? Oh, I don't know, let's say 60. Well, I don't know. 60's a big number. Got a funny look to it. Let's just stay with 3s.
Finding out what's out there. So, how heavy were these black holes? How big were they? The larger black hole was 36 solar masses, meaning it had the mass of...
See, I mean, why should they even be allowed to say something like this? It was 36 solar masses, when they have just almost absolutely nothing to base that on. I mean, almost nothing to base it on as evidence.
36 suns, so I've drawn 36 dots to represent that. This was reported in the scientific paper.
The paper says so. So of course it's a scientific paper. Therefore, it must be true. Just, I mean, just amazing.
Coal was slightly smaller. It had the mass of 29 suns. And then they also measured the...
All right. So you're paying attention, hythloday. This is what they say their masses were. Okay. So this is what they say it was. Not what it was just milliseconds before they crashed or some other crap like that. Nothing from velocities or accelerations. This is how big they were before. And now we're going to get the after number.
Mass of the final merged black hole, which was 62 suns. So everything hangs together. If you take 36 and you add 29, you get 62. It's simple arithmetic. Wow, you guys are good at arithmetic. Yeah, 36 plus 29 is not 62. It's 65. What happened to those 3 suns of mass? Where did they go? Believe it or not, all of those 3 suns of mass, the weight of 3 suns was radiated away in pure energy.
Okay, radiated away in pure energy. So there, at least we get it, right? Radiated away in pure energy. So gravity now is pure energy, right? That's the only way you can add that up, right? They understand it to be energy, right? They understand it. It's in the real universe. It's a real force. You got to account for it. You got to add it up. You know, so it's a conversion of mass into gravity. Nothing Einstein speculated about being possible. They've just made up this new possibility. And why did they do it? Why is this -3 here? Why is that there? If you can see it. Okay? It's there because that equation says that's what you have to do. The only way you can make this happen is you have to somehow make incredible supergravity. It's not just supergravity, it's insanely supergravity. The entire lifetime of a sun, 10 billion years of a sun burning, plus supernovaing, but not supernovaing once. You have to supernova like 1,000 or 1,000,000 times to actually burn every little single element of the mass. You have to convert the mass, every proton, every electron, in a sun. Okay, and release every bit of its energy, which is like, it's like every element of it, every proton is like a little nuclear bomb, in realistically, in terms of how much energy is available to be released between the relationship between protons and electrons. So it's a tremendous amount of energy, and they had to release it in a millisecond to make any of this crap make any sense. Again, if this conversion of 3 suns into pure energy was in the form of photons, we would have been incinerated 5 billion light years away. So it's just by arbitrary circumstance that the universe just happens to do the most powerful energy event that takes place, and it just conveniently does it in a radiation form that doesn't incinerate us. It just wobbles our mirrors. Fuck.
Carried by those gravitational waves. This is E = mc² energy, Einstein's other equation, right?
Okay, so again, he's put gravity back into the universe. All right, so that's good. All right, because Einstein took it out, so they've put it back in. Now it's energy again. It's real energy again. But look what they've done. Just think about the consequences of what they're doing here, and think of the violation of any kind of reasonable understanding of conservation of energy, or any reasonable understanding of what happens when something blows up. What form of energy is it more likely to release, and which form is it going to release first? It's certainly going to release the energy between the electrons and the protons first, and those are the photons. So first you're going to see it. You know.
Except, if you think about the normal way we use E = mc² energy, something really impressive like atomic weaponry, right? Atomic weaponry releases some tiny fraction of the E = mc² energy inside your, warhead.
Yeah, exactly. So it's a tiny fraction that gets released even in a supernova. You've only converted a tiny fraction of the actual mass of that sun into the explosion. If you actually blew up all the mass in that supernova, it would displace half the universe. And that's what they say happened 3 times. The universe was displaced 3 solar masses worth.
Which is not the mass of the sun. Here you're releasing all of the E = mc² energy of 3 suns. That is a ton of energy. And you're releasing that in just a fraction of a second. And in fact, during that fraction of a second when these black holes merge, they're releasing more energy per unit time. They're brighter than the whole rest of the universe combined.
Yes, combined. And again, then you have to average the location, right? Some things are further away, some things are closer. So then you have to average the effect over, and I'm just saying, if you do that, you'll end up still getting a hell of a sunburn from 5 billion light years away.
As theorists, we knew this. Einstein's equations are well established. We know how to solve them on computers.
Again, Einstein never speculated about converting matter into gravity because gravity wasn't part of the E equals mc squared universe. It's bent space, remember? Bent space, it didn't have an energy component. That's why they could make infinite wells that energy falls into. For fuck's sake. Infinite wells that the space falls into. It's not energy.
Calculate that when you merge a 36 and a 29 solar mass black hole, you radiate away 3 solar masses of energy. And we talked about this, but now we've actually observed it happen.
Okay, so I'm just saying, he just said we radiated away 3 solar masses of energy. And I'm just saying there's no rational calculation that you can make to say somehow you can release 3 solar masses of energy and not displace everything anywhere near this thing. Anything anywhere near this thing either gets shattered into dust or it gets moved.
In nature. It's fantastic. Another really fun part of LIGO's story.
Alright, so it's good to do the fun part of the testimony at the trial. You know, we keep it all fun, people. That's the serious scientists do. They just talk about the fun.
Is this amazing signal I've been telling you about, which arrived on my birthday, September 14.
I had to mention that fucking twice, that tripe. Kennedy was shot on my birthday.
They almost missed. The LIGO experiment decided to start their observing run on September 12th. And the founder of LIGO, Ray Weiss, was dragging his feet. He said, oh, it's not quite calibrated, we don't want to start, let's get it perfect. But the younger crowd convinced him to go for it, and we're glad he did, because 2 days after they turned it on, right? This thing's been in the works for 20, 40 years. 2 days after they turned it on, they measured the spectacular signal.
Yes, the spectacular signal. Now they've measured a few unspectacular ones since, and now they have the newest one, which is the 100 seconds of whatever, you know. And again, we don't even get a comparison. One would assume that the signal from the new event has to be somehow an amplitude somewhat weaker since it's so few solar masses. I mean, obviously it is closer, so maybe they just did the simple addition, right? They said, well, 120 million light years. Well, that would be conveniently close enough. You know, some kind of bullshit like that.
They saw something else in October, which is probably a signal, they're not sure yet, and then another confirmed one in December. Then they took the experiment down, upgraded some of the optics, improved the seismic isolation, and we're observing again now. Already, just from one measurement, we learn a little astrophysics. First of all, we learn that black holes can find each other and merge. That's not obvious.
Okay, so they can find each other and merge. So you heard him say it, right? So, I mean, I could come up with some kind of rationale for having a binary system where they start in a binary system, right, as planets or some other kind of thing spinning around each other. But there's no way to create binary systems from the external world. You have to create them like the Earth was created, in a bunch of noise, you know, where a bunch of shit is crashing into each other. Because you have to, it's the only way you can slow the thing down to capture it in an orbit. Things can't get captured in an orbit. They can't stay in a consistent orbit coming from the outside unless they hit something. Without hitting something, there's no chance of ever putting anything in an orbit. You can't throw something from the outside and get it to go into an orbit unless it hits something to slow it down. That's just the facts of, that's Einstein's, that's Newton's gravity. You just can't escape it. From the outside, throwing something into the well, it'll either directly hit the thing in the center, the mass it's interacting with. It'll either just go bend a line straight into it, or it'll miss and shoot back out. Those are the two choices, unless it hits something to slow it down. So there's no black holes finding each other and then spinning unless they're interacting with a third thing somehow. There has to be a third player to fuck the game.
For how many black holes there would be and how often they would merge were all over the map. Now we have height constraints on that. And we really discover a new type of black hole, because previously, from X-ray studies, there in the purple, we knew there were black holes of around 10-15 solar masses. And from other studies, like what Professor Ozell told you about last week, we knew there were giant black holes of a million solar masses.
So they know it. They know it. It's just not like they're, well, we think it might be possible, there's some indication. They're saying we know it. I mean, it's just so obnoxious.
Now we know that there are also 40 and 60 solar mass black holes. So that's the weight of these black holes. But about the size, well, to set the scale, I'll give you a map of the eastern United States. I think that's the part I'd like to blot out, the black holes, right about now. there's the signal I've been telling you about. That's how big those black holes are. There's the candidate signal, and there's the smaller black holes that were also measured. So these are, state-sized objects with the mass of 30, 40, 50, 60 suns.
And somehow density matters. So again, another intuitive argument to, they could do the feathers, the density argument on the moon, and you'll find out that density doesn't make any difference either. Density doesn't change how much you're going to fall in gravity. Doesn't matter how packed your matter is. So they're somehow claiming that somehow this density thing means that from 5 billion light years away, the gravity is somehow different. If the thing is this big and weighs 50 pounds, or it's this big and it weighs 50 pounds, somehow from 5 billion light years away, that's going to matter. Can't possibly matter by any equation that's been scrutinized. It can only matter by something they made up in their little back room.
LIGO is just the beginning. We have 2 detectors, LIGO Hanford and LIGO Livingston. Those are the ones that made the detection, but there are many more detectors around the world, either operational, coming online, being built, or planned. And in 5 to 10 years, we should have all 6 of these detectors working in Germany, the GEO detector, Virgo in Italy, LIGO India in India, and Kagra in Japan.
And all this financed by who, for what purpose? For what? What is this shit?
It's great to have more detectors because gravitational waves are a little bit like sound. You don't really know where a sound is coming from. If you have 2 ears, you can sort of tell where it's coming from, but not very precisely. If you have 3 ears or 4 ears, you can start to tell more precisely, and if you have 6 ears, you can really start to get a good handle on where that sound is coming from. So if we have 6 detectors, we can really tell where in the sky the gravitational wave is coming from, and we can tell our astronomer friends, hey, go point your telescopes over there, you might see something interesting.
Right, and if we go tell them to point their telescopes anywhere, like let's do the experiment. Let's just say any day we just tell everybody, point your telescopes over here, or over there. Let's see if they find something. Yeah, let's see if they do that.
When we have these 6 detectors, and even before, we have a lot of fun ahead of us. We're super excited about the first signal.
They're all super excited. We're super excited. So they say, where do heavy elements come from? Well, apparently it's all the good stuff, the gold and stuff mostly. It's all gold being made by these things. So I guess that's part of the selling point. Like, yeah, well, these neutron stars are making gold. We might be able to get some. What powers gamma ray bursts? So somehow they think they're figuring that out. How does matter behave at nuclear density? So again, as if density somehow changes gravity. How fast can black holes spin? Another question, like, who cares? And was Einstein right? Which is a totally bogus question, because Einstein wouldn't say any of this is theoretically real. He would have said no. Einstein don't do that.
We saw merging black holes, but we're going to see a lot more. I'm sure LIGO has already seen more black holes, although they don't tell people who aren't officially in the collaboration, but I've heard rumors. There are supernova explosions.
They've seen lots of black holes. They've seen more than ever. There's black holes everywhere. Except none of them too close to us, thankfully, right? None of them so close to us that they shatter the Earth into a little bunch of sand. Just aren't we lucky? It's a good thing it keeps happening way over there. Not over there, next to us.
When stars end their lives and explode, they make these giant explosions. That probably makes some gravitational waves. We'll hope to observe those. My personal favorite is Mercury.
Right, but that would be 1 million times weaker, okay, because it wouldn't be burning anything close to a solar mass. Not even 1 solar mass. It wouldn't be even 1/1000th of 1 solar mass. That's how little of the sun blows up in a supernova. Is converted into gravity. In a supernova, it's converted into moving a bunch of matter and creating light. But there's no, the amount of gravity conversion into gravity radiation would be minuscule.
Burning neutron stars. Again, a neutron star is matter at the density of an atomic nucleus. We don't know very much about matter at the density of an atomic nucleus. So we're going to learn a lot of nuclear physics if we can start seeing a lot of merging neutron stars, because those waves carry information about the process of merging.
So again, they say they saw something because of this stupid jiggly line. That's seeing. So we saw it happen because of this jiggly line, and the jiggly line, when we put that in our computer, it creates this wonderful simulation of all this stuff that happened. Yeah, right. That's seeing.
We'll see rotating neutron stars, and perhaps most excitingly is the question mark on the right. Because we've really opened a completely new window on the universe here with gravitational waves. And every other time in the history of astronomy that we've got a new way of looking at the universe, like when radio astronomy started, or X-ray astronomy.
Yeah, right. Yeah, all that stuff had uses besides astronomy, but whatever.
Time there were expectations, and there were huge unexpected discoveries. So perhaps most exciting are the things we don't know about that we will discover with this new way of seeing the universe.
Well, this part's a little bit funny, so hopefully
Change gears a little bit and tell you about my own research.
Hopefully we'll not run out of times.
And one question we asked recently was, what if a black hole spins really fast? You could spin a black hole, and you could spin it really fast. You can't spin it at the speed of light. Nothing can go faster than light, but you can get it really, really, really close, at least in principle. So here's the sound of a waveform that is from a normal black hole. This is theoretically generated. We just made this on our computers as part of the research. But this is...
We just made it on our computers as part of the research. We just make shit up because that's the thing. That's doing good research. Is just to make some shit up.
Just a comparison signal for what a normal black hole merger sounds like. Right, at the end there's that.
So this is kind of funny. It's like the blind leading the blind, in the sense that they have to use audio signals to understand something.
That's the chirp. Chirp is the hallmark, the calling card of merging black holes.
No, it's a bloop, 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 bloop.
Black holes. All the theoretical predictions had always predicted chirps, and that's what LIGO measured.
Yeah, it's bullshit. So again, that's another argument where did that come from? Is there any real documentation that which came first? Yeah.
But when we got one of these black holes spinning really fast, when we finally cracked the mathematics to let us explore this regime, something very interesting happened. It starts the same, but you're not going to hear a chirp from this rapidly spinning black hole.
Oh my God, that was so insightful.
It just sits on a single note and it fades away. We call that a song. It's very different. It's not nip, it's
Ah. Gay much.
So why is this exciting? Well, in astrophysics, we don't have great ways of measuring how fast these black holes spin. But now we can tell that if you hear a sound that doesn't chirp, it just sings, you're looking at a black hole spinning really, really, really fast. Now we gave this...
Yes, and we're not going to get any of the details of how this spin takes all the chirpiness out of the collision. Apparently they'd be spinning the same way, which would end up with a counterclockwise. I mean, the two would be crashing into each other in terms of they'd be repulsive. But whatever.
Black hole, a nickname. And our scientific paper has a funny title up there on the right, In Spiral into Gargantua. If you've seen the movie Interstellar, there's a black hole called Gargantua. And it turns out, for the plot of Interstellar to make any sense at all, that black hole Gargantua has to spin very rapidly. It has to spin with 99.99999999999% the speed of light. 14 nines. So, is Gargantua out there? How would we know? Well, if the next thing LIGO hears, or some other experiment in the future, if the next thing they hear is this song, then we've discovered Gargantua.
Okay, so I don't even know what to say to this mush. I mean, they have their bullshit so far up their ass.
When I started thinking about this problem, I wasn't thinking about astrophysics at all. Rapidly spinning black holes turn out to be a really good theoretical testing ground for the following sort of pure theoretical physics question that I'd like to describe for you. It's called the black hole information paradox. At the start of the talk, I gave you a paradox involving the speed of light being the upper limit that you can physically go, and this formula, V is V1 plus V2.
Right, and that wasn't really a paradox because there's no physical thing in the universe going V1 plus V2. That doesn't happen anywhere.
That paradox was resolved 100 years ago. This paradox is still with us today, and it's really driving theoretical physics, I'd say, more than any other paradox. In its simplest form, the question is, can you tell what was thrown into a black hole? So these are thought experiments, not real experiments, but we used to do them with cats. We would throw the cat into the black hole, and then we started feeling bad about that, so now we use graduate students. That seems to go over a little better. But in these thought experiments, not real experiments, we either throw a cat in or a graduate student in, and then we ask you to come back later and look at the black hole, and can you tell, in principle, not in practice, if it was a cat or a graduate student?
In principle, not in practice. Again, what does that even mean? Like somehow the black hole, it leaves a mark. When you put something in it, it leaves a little mark in the shape of the thing that went in. I mean, it's just such crap.
That I threw in. Einstein's theories say no. The black hole, anything that goes into it, is for all intents and purposes gone from the universe. You will never be able to tell in principle whether I threw in a cat or a graduate student. But there's another theory of physics.
No, Einstein's would say you're not going to be able to tell because it's only mass. You threw mass in. The mass is going to be reorganized and it won't leave a record anywhere that could ever be deciphered of what mass went in. It's just mass.
That you'll hear about a lot more in 2 weeks with Professor Chu's lecture, which is quantum mechanics. And all the formulations of quantum mechanics that we know about have a fundamental law that information is preserved. In quantum mechanics, you have...
No, this is bullshit. So there's no fundamental law. So again, they just make up this crap that there's some law. The law, if there's any kind of law, it's not even what he called it, that information has to be preserved. It's that it's reversible. That whatever the physics is doing, theoretically, you can run it backwards and it'll work. But clearly, we also know that you can't run backwards because you can't create the same you can't run the Rube Gold, just as you can't run the Rube Goldberg backwards, because you can never put the forces in the right locations for it to happen that way. You can't run gravity backwards. You can't run all the things you need to run backwards for it to work going backwards. You can't do.
Have to be able to tell, in principle, if not in practice, whether it was a cat or a graduate student. So there's a fundamental tension here. And it's really Stephen Hawking who first pointed this out after discovering some fantastic properties of black holes that made it very apparent. His paradox is really still with us today. Now, I did not solve this paradox, alas, when I was thinking about rapidly spinning black holes, but it led to a new prediction in astrophysics, which just shows the interconnectedness.
I don't know. So we don't know what the new prediction was, so too bad. Yeah, I don't know what the fuck he's even brought that up for. What did he demonstrate there? Nothing.
It's science. In the last few minutes, I want to take a step back and think about where in the history of science and astronomy this gravitational wave discovery lies. You may know that light is just one wavelength of electromagnetic radiation, and radio and microwave and infrared, and ultraviolet and X-ray and gamma ray are other wavelengths of electromagnetic radiation. There's a whole electromagnetic spectrum. Astronomy really began when Galileo first turned his telescope to the heavens, and among other things discovered the moons of Jupiter. You can see his sketches there. There's Jupiter with 4 little moons that he observed. Since that time, we now have astronomy in all of these different wavelengths. In radio astronomy, we've discovered incredible things. That was the discovery of neutron stars, in fact. Up there in the top left, that speck there is a whole galaxy. That galaxy is shooting out particles moving near the speed of light in a straight line for hundreds of times the galaxy size until they make this beautiful plume that we see in the radio. Some of my other research is aimed at trying to understand what the heck.
Yeah, well, there's something else going on there, but that's full of clouds and shit, buddy.
What's going on there? In the microwave, we can see light left over from after the Big Bang. 13 billion years ago, when the universe was just a hot plasma, no stars, no planets, just hot plasma, no elements even. In the infrared.
Yes, and it's bouncing off of what? Again, where's that radiation coming from? What produced it? How did it get there in the background?
And you can see galaxies, learn about their structure, trace them through cosmic time. In the visible, well, we've come a long way since Galileo. Now, if we look at Jupiter with our best instrument, the Hubble Space Telescope, we get that beautiful image.
It's not exactly the best Hubble image you could have used. I mean, Jupiter's kind of close.
Painted. That's a picture of Jupiter. In the ultraviolet, we can see the storms on the surface of the sun and learn about plasma physics at high temperature. These coronal mass ejections that wipe out communications here on Earth, we can study those, among other things. And in X-ray and gamma ray, we see the high-energy events in the universe. The gamma ray sky looks like that big image on the upper right there, except every once in a while when there's a bright flash, called a gamma ray burst. Those gamma ray bursts were actually first discovered by military satellites looking for Soviet nuclear tests, but they pretty quickly figured out that the gamma rays they were measuring were actually coming from outer space. The origin of those gamma rays is still pretty much a mystery, and it's a mystery LIGO might help unravel.
Yes, sure it will. I mean, you know, just as a practical matter, you're already using up 3 solar masses to make gravity. I mean, you can't. Now you're going to use up a few more solar masses to make a huge gamma ray burst.
But that's the electromagnetic wave spectrum. Gravitational waves also have a spectrum. And where are we in observing this spectrum? Well, we're just like when Galileo first pointed his telescope to the sky. We've made one observation. It's tremendously exciting, these merging black holes, but it's one observation at one tiny frequency band in this whole spectrum. As LIGO becomes more sensitive, we'll start to hear higher frequency things, maybe supernovae and emerging neutron stars. There are space-based detectors in the works that will measure the monsters of the universe, supermassive black holes with millions or billions of times the mass of the sun.
Yes, millions or billions.
There are other detectors that get us to even lower frequencies where we might hear cosmic strings, or if we're very lucky, gravitational waves from the Big Bang itself.
Oh, sure. So that gravity's still bouncing around, moving things.
Let me summarize. I started the evening telling you about how a century ago, Einstein discovered a deep, new reality of interconnected space, time, and gravity. He discovered new things about...
Right, and near his death he lamented that he wasn't at all satisfied with where his work had taken things.
About physics. Those consequences of Einstein's equations were revolutionary, and they're still with us today. And 100 years later, one of those consequences has now been turned into a tool.
So again, he says this has something to do with Einstein, when again Einstein wouldn't be on board with anything Einstein wrote or said. Has nothing consistent with what they're theorizing is the truth. It's not Einstein's work, it's their work. They keep putting Einstein on it just to add credibility, just to say, see, this is Einstein's. We're on Einstein's team, when they're exactly on the opposite team.
We are now using Einstein's gravitational waves to hear the universe.
So again, they're calling them Einstein's gravitational waves. They're not Einstein's. They're theirs. They've made this shit up. Einstein wouldn't draw that little silly gravity popping out of the back end of something. That wouldn't be an Einstein animation. Einstein approved animation. That wouldn't be an Einstein approved animation.
In a completely new way. And in closing, I want to leave you with two questions. What will we learn in the next 100, 200 years with this new astronomy? And what will be the...
Well, know what you're going to find out in the next 100 or 200 years is that you've all been full of shit for an awful long fucking time. And it's because you don't accept any, you're not open in how you do this nonsense. So no one gets to critique at what point you did something silly, like just say, well, if we make the neutron star twice as dense, can't we cut that number in half? Because it's half as big? Huh? And somebody needed to explain to you that density doesn't matter. You can't change something's gravity by making it dense.
The next revolution in space, time, and gravity. Thank you very much.
That was a horrible piece of steaming shit. Okay. So,
Hi, Fred.
Hi, Fred.
Thanks for inviting.
I watched some of these Fred talking about whatever that stupid Pearson guy or Peterson or whatever the fuck he is. Ugh. I hate everybody. Anyway, do I have any time left? No, I don't really. But we'll just jump through this crap. So this is his laughing at video, just more nonsense.
It's home.
Be
This
done with
is a
it.
smaller number than 44, correct? But
So now he's rationalizing where he made the mistake of bringing up something smaller, 33, 44, 100. So he brought up these two numbers, 33 and 100. Now you can't bring up 33 and 100 because they're on opposite sides of 44. You have to bring up numbers that are on the 100 side, not on the lower side. Dumbass.
this is funny. You see, this is old video.
No point in playing old videos, so yeah, go ahead and play your quote miney bullshit game, but anything old video, fuck that.
Objection to wave particle duality and the two-slit experiment back then, in terms of, I would make sure I'm aiming them.
Now, he's quoting me without quoting me, right? So we don't, he sits there, he watches some old video, and then he doesn't even quote what I said. I'm sure I said that if it was possible to aim them, they should be aimed. But I don't know what else I can say to that. So what's your point? Just clearly I've changed a lot of things in terms of my knowledge base has grown over the last 6 years. I keep pointing out how I've watched hundreds of lectures. So yeah, I might have made some errors in these original videos. Now if somebody's going to play my original videos and say, there, I got you because you didn't know something, well, it doesn't matter, because I still was right about the basic theory. And the basic theory and the basic argument that particle gravity was never given a fair shot, because they didn't want it to be true.
To get an equation out of an equation, you need evidence. No, to do that, no, it's a mathematical, pure reason.